In my talk today, I'm going to, as Brianna said, I'm going to talk about 7 things most developers don't know about Windows Azure Blob Storage. And then I'm going to dig into one pattern in a little more detail than the others. Let's see, here we go. So Brianna already gave you that bit. Pretty much coding out loud finds me most places on the web. And very briefly, some of this material, there's a chapter, in fact, on the valet key pattern in this book that I published in the fall of last year, a few months ago. So as Brianna mentioned, I founded the Boston AzureUG group back in October of 2009. So we've been going for about 40 months. So if you're ever in the Boston area, come visit us. Microsoft says I'm a Windows Azure MVP. I'm a consultant, and it's official I'm a consultant because Staples printed some business cards for me. So enough about me. So we're going to talk about blob storage. Quick review. I'm assuming that you know something about it. It isn't going to be a conceptual explanation of it so much as some edge areas, thus the title of some things that, if you know something about blob storage, you may not know these other things. And categories are going to be the different shapes and sizes of blob storage, how HTTP headers still matter with blob storage, talk a little bit about the cost modeling for blob storage and compared to other things, some of the programming considerations, especially some you might not be aware of, the global reach and the robustness of blob storage. We're going to talk about a clever use of blobs for creating a semaphore to span applications in the cloud. We're going to talk about some of the capabilities of Azure that you control programmatically and those that are built into the platform that result in many copies of your data. We'll talk about that across 3 different dimensions. Very briefly, this shouldn't really be 8, it should be 7.5 or something. Some minor comments about safety and security, and that just all those set up. The last thing we'll talk about is the valet key pattern. Now, we have, I believe, 90 minutes. I'm happy to take questions in flight, so you should feel free to get Brianna's attention, who will, I assume, translate the question over to me or whatever, and then I'll also take questions at the end. And this is going to be we're going to look at some of the sources of the data. We'll look at some code snippets and portal. So we're going to be jumping around a little bit. So this won't be a slideshow. So very, very quick review of blob storage. I'm going to start by giving some context of Azure, and then put blob storage in the context there. Now, Brianna, can you see my entire browser, or is it cut off? Okay, good. It was a little ambiguous to me if it was all showing on screen, so thank you. So this is the, if you go to windowsazure.com, and it does this redirect thing here, basically windowsazure.com, and this gives you a nice overview of the platform. So if you click on features of the platform, it has Azure websites. This is hosting for your PHP, ASP.NET, Node. Your WordPress blog can go there. MySQL lives over there. A bunch of things. Virtual machines. This is infrastructure as a service capability. If you're familiar with that buzzword. This is what Amazon Web Services offers, and Azure also offers this.
Duplicate mail, Holly. Being 21 things.
I'm going to mute it. Cloud services. This is the platform as a service model. This is mostly what the theme of my book was. I'm not here to present the book, but that's building, architecting applications in this context. Mobile services, big data, media, and my point here is the Azure platform is very large, very broad, very deep, And many of these other services that are touted as the highest level capabilities of the platform, under the hood, are going to be able to take advantage of blob services, blob storage services, websites, virtual machines. We'll see many of the use cases in here where it comes down to the use of blob storage. So it's a pretty fundamental building block for the rest of the Azure platform. In a nutshell, blob storage is a distributed cloud file system. You can put your files there, and you can reach them through internet protocols, through HTTP, and that's pretty much a pretty crisp summary of it. Anywhere that you have internet connectivity, you can access a blob, a file that lives on Azure Blob Storage out in the cloud. Very simple. And some of the vocabulary here, in order to create or to manage a blob or use blob storage, you first need an Azure storage account. And then within your Azure storage account, you create what is known as a container. That's like a folder or a place to put files. Not strictly speaking a folder. In that folder or container holds your files, holds your blobs. So just by way of giving full context, we're in, this is the Azure portal. So if you have a production, or if you have any assets running in the Azure cloud, you're probably familiar with this portal at manage.windowsazure.com, and you log in here with your live ID, or now called Microsoft ID, credentials to access all of your assets, including blobs, which live in here in the context of other storage accounts. And I happen to have a few storage accounts here, but just for demonstration, you could create a new thing, data service, storage service, quick create. You choose the account you want to create it as part of. I'm going to say, actually, I'm going to choose just a region. We'll say US East, and we'll put it in this account here. And we give it a URL. It's February 13th. And we'll notice this enable geo-replication thing. We'll come back to that, and I'll create storage account. And that's it. It's created, and now I can proceed to create containers within it, and then upload blobs to those containers. So we'll come back to that in a minute there as well. So this is just giving you some context of use of the portal. So we'll put that aside for the moment. We didn't really talk about it. We're not going to. A blob is one of three capabilities that come with a storage account. The other two are Azure Tables, which is a semi-structured database, a NoSQL database, if you're familiar with that. Kind of mentally, you might map it into a structure as loose as Excel, where you don't have a lot of rigor. There's no schema, and that has a lot of interesting capabilities. But that lives in the same storage account as blobs. And there's a queuing facility too, a reliable queuing service that also lives in the same storage account. We're not going to talk further about tables or queues, but you should know that they live in the same place. And also make a comment. This is an iceberg. And my comment about the iceberg is you should think of many of these cloud services, like the Azure storage services and blob storage in particular in this talk, as kind of an iceberg, where the iceberg has a small surface exposed above the water, but the bulk of it, the majority of it, is below the water. You don't see it easily from above. And these APIs that are exposed by Azure Storage for blobs and other things give you a very simple seeming interface into an incredible amount of robust functionality that you can just kind of take for granted. And hopefully you'll appreciate much of what's available to you through the below the surface part of this iceberg by the end of this talk, or perhaps more than you do now. The according to Wikipedia, 1/9 of an iceberg is typically above water. So keep the iceberg metaphor in mind because it's a pretty useful one. So blobs come in different shapes and sizes. So there are two fundamental kinds of blobs. They're not all just files in the cloud. The two significant kinds of blobs are divided into block blobs and page blobs. Block blobs are the ones that you're probably dealing with most commonly if you're dealing with things like putting JPEG files in the cloud, or a AVI movie, or an MP4, or maybe software downloads, HTML pages. Any of these can go in the cloud, and they typically be blocks. And there are page blobs as well. And the difference is the block blobs came out originally, and then they released this thing called the page blob when they talked about when they announced the release of what they called the Windows Azure Drive. So this is the ability to add a durable disk drive to a virtual machine. Back then it was web roles and worker roles and VM role. And you could add and the drives on those are not durable. You could add a durable drive using this Azure Drive thing, and it's backed by blob storage. So it's very robust. Now, the use of block storage for that, Azure blocks for that, would be a fairly inefficient and it just was a non-starter for them to back a drive with blocks because the I/O patterns are so different. So they released a different kind of blob service that is based on what they call page blobs, that is optimized for random access, reads and writes, so all over various parts of the drive, like you would all over the blob, like you would expect from a disk drive. A disk drive,
you can go ahead,
jumps from here to there to
well, I'll go.
to download data or to write data, and these are that's exactly what they've done here. So if we look at briefly at the Azure Drive, go into this data management thing. Various kinds of data management. Tables is what we talked about with in the context of this is also in a storage service. Blobs, we were the main theme. And then you can easily mount the blobs as drives. And basically, it appears to you as an NTFS virtual, an NTFS volume. Enough about that, I guess. And similarly, when I showed the very first slide that showed the high-level capabilities, or the first, the homepage of the WindowsAzure.com, one of the high-level capabilities was Azure Virtual Machines, which I talked about as similar to what Amazon Web Services offers, infrastructure as a service.
No,
and those drives are by default all backed by page blobs, so that they are durable. That's kind of a big important feature as well.
Exactly.
So blobs make
yes, sir.
The Azure Drive and the Azure Virtual Machine possible. So that's 1 out of 7, 2 out of 7. Yes?
Okay. What did they look?
Yep, absolutely. Done. No worries, no worries. You bet. Blobs and HTTP headers. So I mentioned that blobs are, the blob service is a file system in the cloud. But they're also HTTP objects. All blobs are accessed through a REST service, through HTTP, XML over HTTP, and using just regular internet protocols, HTTP or HTTPS. So it's important to think about them as HTTP objects. In particular, a common one to overlook is to serve up a blob, give out a URL to a blob, only to do so without applying a caching header. So let's take a brief look at this. So I say that blobs are available as HTTP objects. They're also available programmatically. So there's an Azure SDK offered by Microsoft. Let me very briefly bring that back. So if you go back to the portal and you click on Develop, you can choose the programming model that you care about. There's also PowerShell, not listed here. And I'm a kind of a C# hacker, so I'd pick on the .NET one, not the Node one or the Python one, for example. And there's an SDK here, and I can install the SDK. And the SDK is language bindings, in my case, C# or .NET more generally. I could access it from VB.NET or F#, for example. And it's bindings that behind the scenes call the REST APIs. So if we looked at an interaction with Fiddler, say, we would see the network traffic when we use the C# language bindings. Similarly with PHP or whatnot. So I want to bring up a particular code snippet here with that in mind. And this very simple code snippet here shows setting of a caching header. So this is .NET Storage SDK 1.7. There's some boilerplate code. I'm not going to really show a lot of. I'm not going to talk about the gory details of a lot of the code because there are great examples on the Azure website. But I do want to call out some particular idioms here. So in this particular example, this is some code that is before doing a file upload of a blob. It's taking a file from the local file system and doing an upload into Azure. It is setting a couple of these properties on it, and these should look familiar to any. First one certainly should look familiar to any web developer, whereas a content type. So this is a blob property, but it gets translated into the HTTP content type header. So that the MIME type, so you know what it is that you're uploading or downloading. And similarly, this is how you would express a cache control header for blob storage. And this one here is set for that max age is 1 year's worth. So if you wanted to cache if you wanted the internet to know that it can cache your company logo ping file for up to a year, that this is how you would express it basically. So there are two kinds of attributes that you can apply to a blob. There are properties and metadata. And either of these properties and metadata can be accessed independent of the blob. So if you had a 100 megabyte video or a 100 gigabyte video for that matter, and you wanted to get at its metadata or properties, you can ask for those without having to download the entire video file. So the kind of the logical mapping here is what Azure calls a property is kind of standard HTTP stuff, and metadata is extra stuff that you can create. And we'll take a very brief peek at that. So this, again, the little inflow code snippet. A property like content type, you can set it to any valid MIME type there, and you call the set properties method. And the set properties method results in a HTTP call back to the server. This rest of the stuff is doesn't actually result in a HTTP call back to the server. So this set properties results in a call to the REST services. And then metadata. So this is stuff that you won't recognize because I just made it up. A job ID or source file name, maybe the source file from the client, when it was uploaded in client time. Like I said, just these can be whatever you want, and it's just a string and a value. And then blob.set metadata will result in a REST call back to Azure Storage to update the blob data with these new values. All right. How are we doing? If there are any questions, certainly give a shout or make a text message or something, and we'll stop and address any questions. So blob economics. So there are 3 different kinds of costs to be aware of when you're doing a cost analysis around the use of blob storage. The three costs are the at-rest cost. If you're not using it, you're just using up storage. Transaction costs, if you're interacting with it. And bandwidth costs, if it's traversing data center boundaries. So let's take a quick peek at those. So the at-rest cost, so this is, you should know about the calculator. So if you go to the Windows Azure portal and you hit on pricing, it'll bring you to the calculator, and there's a general calculator that will help you determine how much your cloud deployment, all the different services together, will run you on a monthly basis. So websites has a free tier, and you can look at the others, virtual machines and so forth. We're going to focus on storage. And notice there are two different kinds of storage here with different prices. And one of them is geo-redundant storage, and another is locally redundant storage. We'll come back to what these mean in a few other points. And the monthly cost, the at-rest cost, is dependent, not surprisingly, on how much data you have stored. So if you want to store 5.75 terabytes of data, it'll cost you about $475 a month at rest for the geo-redundant version. A similar amount of the locally redundant storage would cost you somewhat less. This isn't very good. This is useful for taking your actual usage and figuring out what the total will be. But there are better ways of figuring out, or just looking at a price list. We'll do that in a second. Then the storage transactions. If you use 20 million storage transactions, that'll cost you $2. So let me go back here. I said there were three kinds. So the first one of those, the geo-redundant storage at rest and the locally redundant storage at rest, those were some prices there. The transactions are the second leg, and the transactions are storage operations. So a storage operation means that every API call, every REST API that I invoke against storage, it counts. And they can add up pretty quickly. That's why it's 20 million of them, I think it was, cost $2. Yeah, so they're very inexpensive, but if they do contribute to the cost. So the way that storage transactions can add up a lot is if you're using a page blob as a disk drive, such as in a virtual machine or in a Windows Azure drive. The Azure team actually they decreased by 90% the cost of the storage transaction when the virtual machine infrastructure as a service capability lit up back in June. As a result of that, the cost of a virtual machine was just too high because these storage transactions added up so fast. So every time your operating system did something, or just running your operating system, it's constantly interacting with its disk, which is a blob. So they said instead of before the price adjustment, you would have got 2 million for $2 or 1 million for $1. Now it's you get 10 times that for your buck. So so that's at rest in transactions. And I also said there was a little more sane way of looking at an individual cost, and that is here. This is a little easier to read on if you're looking at the per byte basis. Locally redundant storage and geo-redundant storage. These are the pricing tiers. So first terabyte is well, you can all read them. And they're tiered, so the more you store, the lower the cost per gigabyte goes. These are pretty competitive, and if you look at the cost of the Amazon S3 storage, for example, these will look very competitive because they're very similar pricing. So this is one cost. The transaction prices, as I mentioned, you get 100,000 of them for a penny, or 10 million for $1. And then I mentioned there were three legs in the stool. There was the at-rest cost, the transaction cost, and the bandwidth cost. So the bandwidth is not specific to storage. You don't get charged as a storage cost, but anytime your data leaves the data center, there's a cost. You can transmit data into the data center for free but when your data leaves the data center, you pay a per gigabyte cost. Let me look. I'm looking for egress. I'm sorry, I'm having. Data transfer, there we go. So egress means it's leaving the data center. Ingress means it's coming in. Ingress is free. Azure dropped the price of that. It used to be the same as egress, but they dropped it to $0 last year, and a couple weeks later, Amazon followed suit. But here are the, again, tiered pricing. These zones have to do with geographical location of the data center. We'll talk a little more about the multiple data centers in a little bit. So first 10 terabytes per month, 12 cents per gig, and then down to nickel per gig as you go up. So US is in this zone, and Asia is in this zone. I think Europe is also in this zone. Promotional charge, promotional offer. So that's pricing. A lot of people are surprised by the multiple dimensions of pricing for use of blob storage. Now, if you want to compare those costs to some other costs, that you might appreciate them even further. So if we looked at the cost of a SQL database, which, back to data management. So a SQL database for 100 megabytes, it's going to cost you $5 a month. And 100 megabytes of Azure blob storage is going to cost you pennies per month. And it doesn't get any, the math, the fundamental difference in the math doesn't really change as we go forward. So consider in table storage, that's also in your, these are storage costs in the Azure storage account. So table storage is also in there. So some people, some organizations, it makes sense for them to offload some of their data from a relational database into either table storage or blob storage for long-term kind of archival storage. So that's because the economics are so favorable if you have a ton of data in there. Furthermore, the use of this data is the blob storage is accessible by the Hadoop instance running on the Hadoop services running on Azure called HD Insight. So you can, if you're a heavy user of Hadoop services, you definitely want to be aware of these the storage costs and the transaction costs and so forth. All right, enough about that comparison. And then there's one more. I want to also kind of draw a point here, make a particular point. So if you're using cloud services, which have web roles and worker roles, they also come with some onboard storage in the virtual machine. So if we look at that, so a small, medium, or large, actually, no, I want the cloud services, bear with me, cloud services. The cloud services come with extra small to extra large virtual machine sizes, and they come with instant storage. So 20 gigs on the lowest possible end. This is the 2 cents an hour virtual machine, up to the almost $1 an hour virtual machine that comes with 2 terabytes. So just in case you're looking at these instant storage numbers and saying, wow, that's a convenient place to store a lot of my data, be aware that these are not durable drives. This is not the Azure drive. This is not the kind of drive that the infrastructure as a service virtual machines are backed by. This is not blob backed. So if there's any sort of a failure on one of these machines, your data would be lost. Or if there is Patch Tuesday or some scaled down event where you go from 4 instances to 3, whatever data was on that fourth instance, if it was stored in local instance storage, would be gone. There are good uses for this data, but long-term persistent storage of your critical business data is not one of those good uses. So programming the blob service. We've looked at a few code snippets, and let's consider a couple other factors. So one is that unlike other, I don't know if other cloud or other third-party platforms have this kind of thing, but the Azure Storage Emulator is pretty darn awesome. And I want to take a real brief look at how you might take advantage of that. So this is Visual Studio. And we can do File New. And this assumes that you have the up-to-date tools installed from Web Platform Installer, for example. And if you want to create, I'm going to create a Visual C# project here for the cloud. And you can make it whatever you want. I'm going to simply make it an ASP.NET MVC4 web role. And we can add a worker role and WCF services and a bunch of other stuff if we wanted to, but we're not going to do that here. Generates the project. And by default, we'll give ourselves an Internet app. By default, it creates you an application that is all set to use local storage. This is the cloud emulator, ready to go. And if you can see my screen, I'm down on the bottom right. Usually, you'll get a pop-up in a little icon in the icon area that shows the Azure emulators running. There's one for storage and one for compute. So I'm just going to hit. Actually, I'm not even going to hit F5. I'm going to go into the roles. I'm going to double-click on the one role that we have under the cloud icon next to our cloud project, our cloud, and then the MVC roles down here. We don't care further about the MVC role for this. I'm just going to double-click on that. That'll bring up a little UI that's useful for basically for editing these config files, the cloud, local, service configuration.cloud, service configuration.local, and the service definition file. These files are basically going to be edited when I double-click this. And if I look for enabling diagnostics, it says simply use development storage equals true. That's for all configurations. So if I change that to be the local configuration or the cloud configuration, I can basically click on what's going on. Whoops. So sorry. I don't know why it won't let me make a change. That's funky. All right, I don't know what's going on there, but that's okay. We'll just go over to the cloud configuration file, and we'll notice that this configuration setting is set to the value. This is a well-known value. This is in the Azure documentation that if you set a value here to use development storage equal true, it will use the local development storage. And we can write things to blob storage and so forth locally here. And as long as there's like a database connection string, as long as our connection string is pointing there, they'll go into basically a local version, a local running instance of local DB, or that's the latest one that comes out of the box, or you can still set it up to use SQL Express. Now, what else could this be, you might wonder? So if we actually look at a storage account, and maybe we go to this guy, and we click on Manage Key. Let's say. So this is the portal for, while I'm in here, this is the portal for looking at your Azure storage accounts. there's a dashboard that this one doesn't have any monitoring, but there actually is a nice little monitoring dashboard in here. So you can see it's loading here. These are spinning. So this is some of the use that this has received. These are, you get a little more detailed one over in the monitoring tab. And these are basically the kinds of counters, a moral equivalent of a performance counter that these are tracking. So 100% available for blobs, tables, and queues is not turned on. It tells how many requests it got and so forth. And but we wanted to, you can add metrics and delete metrics and so forth, manage the whole thing here. But we wanted to go and manage the keys, and these are our storage keys. So this key in here, and I can copy it to the clipboard with this little button there. These keys are the things that we would use to replace, they would become part of this value so that they could be used either in the cloud configuration or the local configuration. And again, I'm confused as to why I'm probably doing something silly wrong because I'm doing a demo. I don't know. Like I said, we'll leave that alone. But I should be able to hit that button and paste in the key I just copied and have it override it so that when I deploy to the cloud, it uses my blob storage in the cloud. But when I'm doing things locally, it's using use development storage equals true. So let me put that away now. So that's the so the Azure Storage Emulator allows me to do that. A little note here, recently the Azure team aligned they changed the Azure Storage SDK. This is the C# SDK, or .NET SDK, that insulates the developer from having to deal directly with REST services, and everything looks like a class. And that's kind of the snippets of code that I showed so far, and I'll show a couple more. They made some changes to that to align it more style-wise to the Windows RT APIs. So there were some incompatible changes that occurred between versions 1.7 and 1.8. This is recent, a few months ago. I am in the process of upgrading some my code for various projects to 1.8 opportunistically. So beware that some of the code that I'm going to show you today or have already showed you might not yet be migrated to 1.8. Most of the code's the same, works the same, but there may be a few things that have changed just a little bit. So you need to be aware of that. Now, one of the aspects of programming the blob service that surprises people is that blobs are, it's a multi-tenant service, one thing. So that means that my storage data, my image files and videos and text files and so forth, are stored on the same machines in the same drives as yours and the person next to you's. It's multi-tenant. Lots of people get to use it. And it's also built on commodity hardware. This is also surprising. So commodity hardware is hardware that's pretty good, but it's not the highest end hardware, and it's not low end junk hardware, but it's hardware chosen specifically because the bang for the buck is higher, meaning that the highest value is achieved by purchasing and going with commodity hardware. As you get to higher and higher end hardware, like with redundant hardware, for example, like maybe RAID drives that have a level of redundancy or multiple power supplies and basically hardware that's designed to not fail, there's an expense to that. And also, as you get higher end hardware in terms of just faster, like the fastest CPU available today or the highest density memory available today, comes at a premium cost. So the public cloud vendors like Microsoft and Amazon and Google and others have realized this, and they've taken other approaches to securing your data that is not just having hardware that won't fail or spending a lot on hardware. They've focused on highest value. So one of the consequences of this, of these two items being multi-tenant and being on commodity hardware, is that unlike when you're writing to a local disk drive, sometimes the API call that you're calling to save data or read data will not succeed. And you may get a rejection. Basically, there are a couple of different ways this can happen, but the most popular one is just busy signal pattern. And you're returned an HTTP status code that says essentially, hey, I'm a little overwhelmed at the moment. Can you try again in a few seconds? Or maybe in a few milliseconds even. And usually when you retry, it just works and everything's hunky-dory. So you have this notion, this responsibility on the client that you have to be prepared for the cloud to have these what we call transient failures, and you have to react accordingly. So along those lines, Azure SDKs come with some standard retry policies, and if you do absolutely nothing, you just use the SDK out of the box, and you write code that reads or writes blobs, it behind the scenes is already by default configured to retry up to 3 times, and with a what's called an exponential backoff. So the simplest retry is to just retry right away and just keep doing that. A little more sophisticated retry is to recognize that, well, there's probably a reason I'm retrying because the service is a little bit hot at the moment. And so this is a linear backoff. So you might wait half of a second before you retry, and then wait another half of a second if you have to retry again, that kind of thing. Then there's also an even more forgiving one, which is known as exponential backoff, which retries after, say, a quarter of a second. Then if that doesn't work, it'll retry again after another half a second, and then again after that after a full second, and so forth. You can see that the retry interval is doubling each time. And furthermore, you can have custom retry policies. For me, I haven't really found that a custom retry policy is needed because I thought of a new retry approach, like random retry or something. That actually might be a decent one, frankly. But that's not why I did it. But I did write a custom retry policy for a project because I was uploading a ton of data and I wanted logging. I wanted to know how often I was actually doing a retry. And the link to this is in there. But basically, I create a custom retry policy, and it's just like the exponential backoff that comes with the SDK. So it just mimics that. There's nothing different in that regard, except that it allows me to do some logging, and I can calculate some statistics and so forth. So you can look at this if you wish, but just the useful thing for me again was that it logged it, and I knew that in my giant log file, I had a process that ran for more than a week, uploading terabytes worth of data, and it would tell me that it would go for great stretches without any retries. Then there would be an occasional retry, and sometimes there were a lot of retries. So that allowed me to keep tabs on things. So that's custom retry policies. And another sort of retry that I've encountered occasionally is it has to do with containers. So I mentioned that within your storage account, you can have blobs, but the blobs always live in a container, just like in a file system, a file always lives in a directory or a folder. And Azure has a consistency model, which is known as strongly consistent. Fully consistent, there's a few various names for it, but it's the opposite of eventually consistent. An eventually consistent model is one where you might save data, and then if you read the data back right away, you might get the old data. And typically an eventually consistent model spans a very short amount of time, like a fraction of a second. So it's not like your data is going to be stale for hours. But Azure, for the storage subsystem, they've chosen to use a strongly consistent model so that you are guaranteed that after you write it successfully and read it back, that it will be the same thing that you wrote. There's one little funny bug or behavior. I don't think it's a bug. I think it's documented. Is that if you delete? So this has the strongly consistent part applies very nicely and consistently with blobs. But if you ever delete a container and then recreate a container with the same name, that container name is not available for a short amount of time. There's some sort of a garbage collection going on. So if that ever, if you ever need to overcome that, I've written this I've used on a couple of projects as well, is patiently create a blob container where this takes that into account and handles the right exceptions to determine that that this is not another kind of failure. This is actually the kind of failure that happens when Azure is trying to recreate a blob container name and the old one hasn't fully gone away. So again, using the storage client SDK in C# code here, and create if not exist. Some of these have changed subtly. There's an S there now in the new SDK, and this is client. This is not storage client exception, just storage exception. They've cleaned up a few things, took the opportunity to do that in the 1.8 one that I mentioned. But anyhow, that does what I just said. It will keep going until, for half a second or a few seconds until it's able to fully create the new container name. So those are some new some thoughts about programming the blob service. Now let's talk about blobs having reach. So the blob service itself is available in 8 data centers, and these are the 8 Azure data centers. There are 4 of them in the US, 2 in Europe, 2 in Asia. So let's take a peek at that. So if we go to the management portal, let's go to manage.windows-azure.com. And what I want to look at is creating a new Azure blob account, and I want to point out the options that are available there. So if we go to the storage service here, those are existing ones. I'm going to create a new one, and it's data service, storage, quick create, and again, I choose data center. So this is the point I wanted to make. There are these 8 data centers: West Europe, Southeast Asia, East Asia. So 2 Asia. Oops, 2 Asia. 2 Europe. That's West Europe and North Europe. The West Europe and North Europe ones are in Dublin and Amsterdam. The Asia one's in Singapore. I think the other might be in Hong Kong. And then the South Central and North Central U.S. are in Chicago and San Antonio. And then East and West are in Virginia and might be Washington or something for the West one. And another dimension of this is these are actually paired. This becomes important in a minute. So East and West are paired in the U.S. South Central U.S. and North Central U.S. are paired. North Europe and West Europe are paired, and Southeast Asia and East Asia are paired. And each of these pairs are geographically separated, and they're in the same geopolitical region. So sometimes there are data issues that have to do with your data moving out of, say, the EU or out of the US with certain regulatory compliance issues. So that's an important thing to understand. We'll talk about that again in the context of, in the next bullet point, the next number 6, in the context of making copies. Now, Azure also has a content delivery network built into the platform. So you can CDN enable a blob your blob storage. And the CDN, for those who aren't aware of it, is a content delivery network. That's the full name. And the content delivery network consists of 24 nodes around the world, or points of presence. And these include the 8 data centers, and there are 16 additional ones that are geographically distributed, Australia and South America and a number of other places. And these are cache nodes, essentially, that will store a copy of the data that was requested from your blob in a local storage system, a CDN cache, a point of presence in, say, Chile, say, and anybody else who is close to that point of presence who requests that same data will be able to get it from the much closer CDN point of presence, improving performance. It uses Anycast DNS, which is a standard DNS thing that says, hey, what's the closest DNS server or what's the first DNS server that answers my DNS request, my DNS lookup? And that's how it knows which of the 24 POPs is closest. I'm doing air quotes here with closest because it's not necessarily the geographically closest. It might be a further away one that just has a better internet connection or less congested internet connectivity to that point. And this is pretty powerful. You just turn on the CDN. However, the CDN only applies to public blobs. And we haven't really talked about that yet. We'll get into it in the valet key pattern. But a blob is either protected or it's public. And the CDN only applies to blobs that are public. And furthermore, the headers, the HTTP stuff that we talked about earlier, setting cache headers and so forth, that still applies here. So any HTTP headers like a cache expiration or MIME type and so forth, these carry into the CDN, and the caching one in particular governs how long it would be cached in the CDN. So pretty powerful that you can, with a couple of clicks of the mouse, say, I want to just enable CDN access. So that helps you with global scale. Now, another aspect of being built to scale, so we have the 8 data centers distributed around the major commerce points in the world. We have the additional 16 CDN points of presence, and all 8 also serve as CDN points of presence, all 8 data centers. Great dimensions, and there's still one other dimension. And I want to point out that these 2 blog posts are similar in concept, where they're trying to talk about the scalability targets of Windows Azure storage generally. And they were updated recently, just a couple months ago, with a new flat network architecture that has extensively enhanced the overall scalability and capacity of the blob and more generally the storage platform. So let's take a peek at that. So Brad Calder is the big brain at Microsoft who runs the storage world there for Azure. And I just want to go, so these are some of the differences between the Gen 1 and the Gen 2. So we're on Gen 2, that's the flat network one. And they've gone to software load balancers instead of hardware because they're more reliable and they could be updated more easily. They use solid state drives for their journaling instead of more traditional moving head hard drives. The network is flat, so it's not hierarchical, which has more hops. And they've increased the storage speed from 1 gigabits per second into up to 10. So that's pretty huge leaps. And as part of this leap, they've upped the capacity from 100 to 200 terabytes, and the transactions, I think this was 5,000 entities per second or blobs per second, and now it's 20,000. So with the new architecture, they've really made some great enhancements. And this is bandwidth for the geo-redundant storage and locally redundant storage. So you can bring into the data center 5 gigabits of geo-redundant. You can exit the data center at about 10 gigabits per second. These are account level scalability targets, and they're the ones for locally redundant, a little higher, a lot higher. So this is some pretty badass scalable stuff. and you get it like remember the iceberg. You just start using these things, and you get all these features just out of the box, which is pretty impressive. Which makes the cost all the more palatable. Good costs. So as we go into making copies, number 6 here, we have. I want to get into talking about what the difference is, why it matters with this locally redundant and where'd it go? The locally redundant. Here we go. Yeah, the geo-redundant and locally redundant storage. What these differences are. So the locally redundant storage. This is the minimum that you can access with Azure. So I talked earlier about the Azure storage model is not eventually consistent. It's strongly consistent. And that strong consistency is designed to span 3 physical nodes. And by this, I mean, if you are this has to do with writing data. If you are writing data using the SDK, or the REST APIs directly, or the PHP API, any of these things, they're all backed by the same REST API, then before the REST API will return to you a success, it will have guaranteed that you have saved 3 copies. It will have saved 3 copies of every byte that you just asked it to write. So if you've asked it to write, say, a 4 megabyte block of data, it will have saved that 4 megabytes, each byte in that 4 megabytes, in 3 separate places on 3 different machines, on 3 different hard drives. And it's doing this in part in reaction to the opportunity of building a data center on commodity hardware. So this is a pretty big deal. So rather than having high-end hardware that doesn't fail, because we have a bunch of RAID drives or whatever, super redundant RAID, rather than doing that, the more expensive route, the higher-end route, the higher ceremony route, they've gone with this lower ceremony, more cost-efficient mechanism that they call that this local redundancy that basically writes 3 copies, and they expect that they will fail. One of those 3 copies will be lost because the machine it's running on just melted down. It's the hard drive was end of life, or there was a memory chip fried, or something. And somebody spilled coffee on it, maybe. That's less likely than you think, because I don't think they have humans very often trolling around those data centers, but you get the idea. So the idea is that if one of the 3 copies goes bad, they just create a new one. If that drive fails, they just, the operating system that runs storage says, we're down to 2 copies. We better replicate from the 2 good ones right away so that we have a 3rd copy. And data loss is prevented by keeping 3 copies on local commodity hardware. Now, beyond that, there's another level, which is geo-replication. And this is what distinguishes locally redundant versus geo-redundant storage. The locally redundant is stored 3 times locally. The geo-replicated, geo-redundant storage is actually replicated to the sister data center, and another 3 copies will live there. And this happens transparently to you. It is not strongly consistent like the locally redundant is. When that API call returns, the 3 locally redundant copies are written, but the geo-replicated copies are not written. Those happen asynchronously in the background. I've never heard an SLA or a guarantee on that, but the number I hear is a few minutes, maybe up to 5 minutes for the geo-rep to happen. And this makes sense, right? You don't want to, your application performance would sink pretty bad if it had to wait for a geo-redundant copy to be laid down on a platter, 500 miles away. That wouldn't scale very well. So that's why they choose that model. Now, the geo-replication aspect is really a DR model, and it's for Microsoft DR right now. There's been talk of giving you access to the geo-replicated copy for business needs, so you can write it to 1 and read it from 2. but that has not lit up yet. And that's speculative. But as a speculator, I would guess that's going to light up in the near foreseeable future. I would guess, so that you could get at those sister copies. Well, another thing that you cannot do is you cannot you as a customer, you cannot force a failover. So this is in place so that if a tsunami hits one of the U.S. East data center, then Microsoft can pull the big switch and fail over the whole data center to U.S. West, the sister data center, and everybody gets DNS gets rerouted and everything just wakes up over in the other data center. This is total loss kind of DR. You have no control over that. That's entirely in Microsoft's control. And as far as I know, that switch has never been thrown for any reason on any of those data centers for customer data. There is rumor that they might add the capability that you can actually manage the failover yourself. So there's some limitations of it, but the fact that you have 6 copies of your data for the price of 1 is pretty cool. Now there's another mechanism that's available in Azure that is under programmatic control, and this is snapshots within a blob. This is pretty interesting. And a lot of people don't know about this. So I'm going to go over to the Cerebrata tool here, and we're going to look at. So I have couple storage accounts here, and I have a couple of containers within it. I'm sorry, this is a list of storage accounts. There's one storage account, and here are my blob containers. I have one container called Kayak Photos, and it has one blob within it. Now, if I right-click on this blob, I can say snapshot. And of course, this is all available programmatically, but it's easy to use the Cerebrata tool, which is a great tool. This should be Azure Management Studio. This should be in your toolbox if you're an Azure developer. So I'm going to say View Snapshot, and I can see that I have a snapshot that I took earlier today. And I'm going to, just to show you what I'm doing here, I'm going to take another snapshot and make another copy of it down here. So a snapshot is basically versioning. So so it's the same file, the same blob slot within the container, but it can have multiple snapshots of that blob. So, for example, consider if you were building a source control system for software developers, you may want to use a capability like this, where every time somebody does an update, you basically take a snapshot of the existing one before you allow them to overwrite the most recent copy with the latest code, and you can access these earlier snapshots. So or Word documents, or maybe you keep your monthly reports in the same place. You want the same URL to be able to access them for some reason, and but you don't want to lose the history. And you could actually rig that up with snapshots pretty nicely. So when you ever went to the URL, you always get the latest one. But if somebody ever needed to go backwards, there was a way to do that, and the data was retained. Now I say in the slide deck here that this is efficient pricing. So a blob is built up of smaller chunks. So, for example, if you were uploading a 100 gigabyte blob, then you wouldn't do it in one HTTP post request. You would do it in chunks of probably 4 megabytes. And so there's the granularity there is the granularity of the price difference. So if you have a blob that has, say, 100 of these chunks in it, and the change delta was only in 2 of the chunks, then you would only pay for the pricing difference in those 2 chunks. So since for example, I just made 2 replicas of this that are identical because I didn't actually make any changes to them, then I shouldn't be paying anything extra for these because there are no differences. Now, if I changed something within it and then uploaded it, again, I would, and I only changed one of the 4K chunks, say, I would just pay the cost of the original plus whatever the cost is for 4 megabytes for a month. That's what I mean by efficient pricing. Now, another cool use for blobs, and this is the final thing that on the list of things that most people, many developers may not know about Azure blobs, is you can use it for a semaphore, where I think we can let Google tell us what a semaphore is. Whoops. Oh, well, that's interesting. So, well, anyway, a semaphore is, you may be familiar with the concept of a semaphore flag. It's a flag that you can use for signaling from one place to another. And in code terms, programming terms, a semaphore is often a technique for coordinating work across two processes that wouldn't otherwise know how to interact. So you don't want them stomping on each other. So you put a flag in the middle that one of the processes can hold up and say, you know, I want to do this, or I've done this, and now you can go ahead, and they lower the flag, that kind of thing. And one of the kinds of semaphores is a counting semaphore. So this is a snippet of code, this blob semaphore, that I've used to coordinate a very simple task, which is I have many instances of a process running in the cloud. That's easy to do. And I want them to each have, or each generate, a unique identification number for some of the work that they're creating. So in this case, this particular snippet is dealing with a job ID. And there are various ways of doing that. And this blob approach that I'm showing you here is one way. What this is doing is it's got a well-known blob in memory. It's got a specific blob that's well-known to two parties or n parties. And whenever one of the parties wishes to get the next job ID, they want to get, you know, the next number, and they don't want anybody else to have a duplicate number, they lock the well-known blob. They grab its contents, and it contains the number, you know, 1, 2, 3, say, and they increment it to 1, 2, 4, and they write it back. And Blob has nice support for this in its leasing functionality here that I've just highlighted on screen. And this leasing functionality says, I would like exclusive access to this. And so if any of the other processes attempt to create a lease during the time where I've leased it, they should be put on hold. And this is the basic easy, cross-process way in the cloud of achieving this. This lease is a very handy feature. So let me look at the code. Let's look at the code here together. So you need to initialize it at some point. This basically just uploads the number 0 or something into a blob. Call that once. And then forever, for the rest of the time, you call get me a unique job ID. And probably some of this boilerplate stuff you don't really need if this is being called repeatedly. But this is standard stuff that you see frequently, that to make sure that the container and the blob exist, and could create them if they don't. But in our case, it will always exist. So we pretty much start here. It's creating a random time interval. Time before retries is now, that's the starting time before we did any retries. That's for, I believe, just for logging purposes. And then we've initialized our lease to null, and we're going to retry up to 100 times and up to 2 minutes. And we'll try to this is a straightforward SDK call with a REST call behind the scenes. And the default is 60 seconds. Give us a lease, acquire the lease. And if it doesn't work, we catch it. We do some sleeping, some fancy stuff here to make sure we're not beating on the thing if somebody else has it, because it might take them a couple of seconds to finish with it. And then we just keep retrying here. If we've acquired the lease, then we increment the string to the next one. There's a string in the blob that we're treating as an int in this case. we increment it, and we write it back. If we want to keep it as plain text, the content type, every time you write the value, you're overwriting also some of the metadata. So if you want to keep the content type consistent, you may want to write it every time and set the properties. Then you release the release when you're done, and then you've got your job ID, and you return that to the rest of your code to keep going. So this is not a necessarily a super fast, scalable way to do it. Like if you had many jobs who needed thousands of these per second, this probably wouldn't be a very good approach. This is better for the occasional coordination task. And in this particular case, this code was serving a use case where there were high-level jobs being created, and these jobs would take about 30 minutes to run, and they came in, sometimes a few in a second would be a lot. So it was kind of low, but a pretty robust way to do it, because you have this nice semaphore that you can use across processes, even across data centers. Pretty flexible in that regard. All right. Safe and secure. So this is nothing super crazy complex here, but just a little bit of a reminder. So we have keys to guard a security account, a storage account, and let's take a quick peek back at those. So these were these. We have two. We have a primary access key and a secondary access key, and you have two. And if you're programmatically accessing blob storage, you need one or the other. And from a functional point of view, they are equivalent. There's nothing that you can do with the primary access key that you cannot do with the secondary access key, and vice versa. You have two, which allows you to do a more managed update of these keys. So if I have code that is using one of these, and it's time my security policies, or there's some event that causes me to want to modify the key, then I can do so first. I can regenerate one of the keys, and then I can come back to it and come back to the. So suppose my code is using the primary access key. I can first replace it with the secondary key. Then I can go recycle the primary access key, or I can give some of these to some customers and some not, and some to others, knowing that I'm going to want to invalidate it. But if you're sharing this with customers, there's actually a much better way that we're going to look at in a minute with the valet key pattern. But just saying it out there, these are just putting it out there. These are cryptographic keys that the platform is created on your behalf. You should treat them as very important data to protect, similar to a database connection string, username, password kind of stuff, because access to these gives somebody complete and unfettered access to everything in that particular storage account. You've been warned. Also like to point out HTTP and HTTPS. So all the API calls that you make against storage, they can travel over HTTP or HTTPS. It's your call, literally. Either one works fine. If you're passing, if in the valet key pattern, as you'll see, you're almost always going to want to pass pass things with HTTPS, because the availability of just access to a HTTP URL is decisive. With a valet key pattern, you won't need the storage credentials that we just looked at in order to do damage. So let's now look at how the valet key pattern extends this idea of securing your keys, securing your storage to your clients. So first, the metaphor. A valet key is a special key that comes with modern cars, and I'm from Boston. I have to work to say car instead of car. The valet key allows you to give the key to an untrusted third party, like the valet parking dude at the nice restaurant, and it allows them to access to certain functions of your car without full access to it. So, for example, a valet key can turn on the ignition and allow you to perhaps unlock the door, but it will not give you access to unlocking the trunk or the boot, depending on what part of the world you're from, and probably not the glove box or on the inside that might have other kind of confidential stuff in it. So it allows you to control some aspects and give you enough confidence that you can give somebody your car to park without you worrying about them rummaging through private areas. So this is extended in a great way, in many, many ways, through the valet key pattern as it's available through Windows Azure blob storage. So I mentioned earlier that that you can, through a very simple configuration change, you can enable your blobs to be CDN enabled, but they had to be public blobs. So that's one valid kind of valet key pattern as well, is that you can just make your blobs public, but that really doesn't give you any sort of granularity. So we could go back to the Cerebrata tool, and we could make a container like this. We can change its permissions. This one is it's public read access. So anybody can read this zip file out of this container if I give them the HTTP URL to it. We can also make changes to it. We can make the container private, or we can change the access so that so it's at the blob level, not the container level. And we can furthermore demo gods aren't with me today. You can furthermore update the permissions of individual blobs. All right, let me go back here. This is what I want to do. So you can make them public read only. That's easy to do. But any other scenario where if you want to make it writable, whether public or not, or listable, whether public or not, these are valet key scenarios, and these require a different approach. The different approach allows you to do these kinds of things. I want to list the contents of a blob. This only has one in it, but if I want to give somebody the ability to iterate through them and look at them, I can do that with a valet key. I want to be able to read the ones that can in the blob container. I want to read a specific blob. I want to write to a container or update a specific blob or delete a specific blob. These are all kind of very focused permissions. I can give you a valet key. I can give him a valet key to write to a specific blob, and I can give her a valet key to write to a specific different blob. And his valet key will not work on her blob, and hers will not work on his blob. And these permissions available in the valet key can also have start times and end times, optionally. So I can give somebody permission to update a blob, but that permission expires at 5 o'clock in the evening. Server time, by the way. So this is not manipulatable by client-side code. This time is enforced on the server. So these are really, really powerful. Let's look at a couple of scenarios that that I've actually used this pattern with, and I actually used it 4 times, and then I said, "Wow, there's a nice pattern there," and this is there's a chapter on it in the Cloud book. So I had a client that had an add-in to a desktop application, and they wished to beam a very large file into the cloud for extensive processing. This was a startup with a software as a service product that was used by building architects, and it was very clean to devise a mechanism where a very low complexity, low volume web service could issue these valet keys. So the add-in from the user's desktop would make a very quick call to a WCF service, and it would get back basically just a URL. And then with that URL, it was able to take its time uploading a very large file. And the uploading of that very large file did not negatively impact the performance of that WCF endpoint, because the blob storage capacity that we looked at when we looked at the scalability targets blog post was taking care of those needs, and the WCF service could be a very small instance with very, very humble scalability targets, because it's what it did was very surgical and very small. So it's very useful. Another one, I helped a genealogy site build some software that would allow users to look at images of genealogical data, but they were afraid that the site would be too easily crawled, and they didn't want somebody downloading their many, many terabytes of data, because it would be on their dime, right? If somebody downloads a terabyte of data from your storage account because you let them, you get to pay for that. So the opposite kind of valet key scenario was used, where they were given a read-only URL, and it had a time limit. And that worked very nicely and did a really good job of hampering the ability to do crawls, because the blobs were never directly visible to the customers. Bandwidth saving. So the kind of with the architect add-in example that I gave first, one of the benefits of this is the bandwidth savings. In another case that a client now has a situation where they are doing a lot of uploads in the middle of the night, and they want to really optimize the costs of that. And it looks now like we're able to do it on an extra small role instance, 2 cents an hour deal, where, because again, all the processing, all the upload power is handled by Azure Blob Storage. So it would cost you the same from bandwidth point of view and storage transactions point of view if the blobs came through your web role, and then the web role wrote them to blob storage, versus going directly to blob storage. But the two disadvantages of that are that it adds a significant scale burden to your web roles. So in this case that I'm talking about here, they would have had to have much larger web roles to handle the load. But as it is, these are similar to the add-in case. They could be very tiny web roles that are just handing out valet keys, basically generating URLs and handing them out, and then it's up to the client to upload directly to blob storage. And the other, well, that's a pretty huge benefit. So I'm going to basically just wave my hand at this last one. There were also regulatory benefits. I've been talking to a customer with temperature sensors, and this can be used to help them guarantee their compliance, because they have to be able to prove that these that sensor data was not updated during certain times, and they can prove that with valet key signatures that are time bound. And this is just a little bit of a visual. You get, if you, instead of going to, so another one here is you can have the canonical photo upload from an iPhone, and you don't want to have to go through your web tier, and you want it to go directly to blob storage because it's more scalable. It's less costly because your web tier can be smaller relative to what you'd have to handle with this, and the reliability is better. The blobs, you take one of the middlemen out, and you let the blob robustness take over. Now, the mechanics of generating a valet key, I'm going to speed up here because we're almost out of time. It just uses the primary or secondary access key. There's no network call or anything. It's a cryptographic inline generation that basically you give it the parameters you want, read or write or list or delete or whatever, and then the start time and the end time if you want, and then you sign it with the key, and then it becomes valid, and that's checked on the server side. Now, just for the sake of expedience, there's also very quickly there's you can. So what I just talked about so far is a signature that once you send it out, you can't change it. But you can also create what are called access policies, and I think you're limited to it's either 3 or 5. I'm not remembering. But these are policies that have a name like overnight upload or contest, and then they have all the same parameters: a start date, an end date, read, write, delete, or list permissions, whatever you want. And you can give them out signed to the name of the access policy. And then after they've been issued, you can go and change the access policy. And then, so basically you've influenced the effective permissions of everybody because of that. So that's a pretty cool way to manage it even after you've shipped them. And I have a valet key pattern code library in the works. And I'm working with a friend of mine who is more of a cross-platform guy, because you can do some of the same things on Amazon S3. They have some of the same capabilities in the storage. And also, as of the fall, Azure supports this same pattern for queues and tables, which is pretty cool. So you can do a shared access signature for, say, a queue, and a queue mechanism. So with that, I'm going to stop. And I think I'm going to turn it back to Brianna, and I'll let her finish up. We are going to give some book away.